Quantum force fields come from the spin 1 field, which are part of the open strings theory. Before, we talked about the closed strings and how that leads to general relativity over here, and how we also grab a spin 0 field trace, which is just a scalar field, which is nice. So we have these three fields that we can work with. We have the spin 0, which is just the scalar. That's just adding up these numbers right here, at y and the z, and then we add it all up and we get a number, which is cool. So this is just a field value at each coordinate. Say you could call it like temperature or potential. You could use these numbers to describe temperature and potential. The spin 1 is these vectors. So, t, x, y, z, it's a vector. It gives us access to vector fields. So we can talk about field amplitudes at each coordinate. That might be the electromagnetic field or any other kind of force field. And so the spin 2 was just the geometry of the coordinate system. That was just going to be this massive tensor right here, which is the matrix. It describes the geometry of the coordinate system, and these two fields describe the values and the amplitudes at those coordinates. That's spin 0 and spin 1. So those are the quantum fields. Now here's something interesting we could take a look at, which is how these strings can interact together. So you can kind of approach, combine, and separate. Over here, we can exchange gravitational information by forming a closed string, and over here they can combine into a longer open string like this, and that could be a particle interaction, and then they separate. But what's important is that we need to be able to describe rotations, because that's where the gauges and the quantum fields show up. So the fields are described by a Lorentz rep and a gauge rep. These are just representations of the types of groups that we can use. So the rotations in the Lorentz presentation, this is just vectors. This is just vector rotations. So they have to be able to rotate around a time dimension and 3 dimensions of space. So this is how we'd use the special orthogonal group, and these are the Lorentz boosts and rotations. So this is just the basic special relativity actions right here, rotations in regular space. But at each point in space, just like there was a scalar field, just like there's a vector field, and just like there's the curvature at each point, well, there's also a gauge internal fiber at each point as well. And these internal fibers, well, we have we can imagine them as complex helixes, meaning they're spinning around in the complex plane. So they're both real and imaginary helixes. And so we can look at them as like one-strand helixes, two-strand helixes, and three-strand helixes. And this is going to represent the groups U1, SU2, and SU3. So those are going to be the strands, the internal strands that we can attach to every point in space-time, and this is going to give us the standard model. So all we need to do is to basically take some tensor products, so we could say 1 times 1 is equal to 1, and that gives us one gauge boson. So that's going to be one matrix, essentially, or one element, and this leads to electromagnetism. Electromagnetism is in one dimension, and we just get this e to the I theta equals 1 magnitude. This is just a complex rotation in regular old angle here. Boom, boom, and here's the angle between it. And then the magnitude of this vector stays the same. The lengths here are the same. So all we've done is basically, we require like photons and stuff to be able to do this. So when photons act at each point, we use the single strand helix right here, single strand helix, and we get e to the I theta. So this is how we can act on the vector field right here. This is a vector. And so that was U1. Now we can go to SU2. So SU2 is the double helix here, and that's just going to be a 2 by 2. So we multiply those together and we ask ourselves, how does this add up? Well, it adds in 1 and 3. So what does this mean is we have 3 gauge bosons right here. Those are going to be the W bosons. The W bosons. Those are these ones right here. So the W bosons is going to be W plus, W minus, and W zero. Okay, so it's kind of cool. But we have the idea is that on the left side we have one trace. Okay, so we're able to like add this up. So here is the one that we can trace. So we can trace this up, and 1 plus 1 is going to be equal to, add up the diagonal components, and we get 2. Okay, and then we have three traceless. So this is where we have the traceless ones. You add up the diagonal components here, it's 0, and then 0, and then 0. 1 minus 1 is 0. So these are the traceless matrices, which are the W bosons, the Pauling matrices. And so this gives us the weak force right here, the 2 by 2. And that's going to be like this little two-strand helix. And the 3 by 3, well, it's just a little bit more extended version of the 2 by 2. So it's going to be like 8 gauge bosons, but we have one trace, and here are the 8 traceless Galvan matrices. I didn't even write them out because it's just basically bigger versions of these 2 by 2s. So that's going to lead to the strong force, which holds the quarks together in their particles. So, you know, you have like a neutron, and these things are always going to be like an up, up, down. That's going to be sort of held in the neutron, and that's what the strong force does, and it changes their colors. So these are going to be there are red, green, and blue colors, and so that's essentially what the three strands are representing, the three colors. I mean, these are how we're able to calculate things in the standard model. So let's make sure that we can see this right here. Uh, So here's how the strong force works. It's just going to be neutrons, you know, up, up, down. We have the red, green, blue colors, and this is the weak force right here, which flips things from, like, say, the electron to the electron neutrino. Boom, you could decide which one of those you want, kind of flip those back and forth. And these are the three quantum forces: electromagnetism, weak force, and the strong force. Boom. How interesting. And this just pops out of these three different helix looking structures. They're complex helixes because they're doing rotations in 1, 2, and 3 dimensions, and complex dimensions, really. So that's cool. These are just internal fiber strands. Fiber strands. So this is how the quantum field theories start to emerge from string theory. And all we needed was the open strings because that gives us the vector field. And with the vector field, we could start doing rotations on in 1, 2, and 3 dimensions. Cool. Hopefully this was interesting and y'all have an awesome